Chapter 26 and 27 are our resistance chapters and resistor circuit chapters. In chapter 26, we're going to get really basic, like sort of like when we started with capacitance, like what are the fundamental properties of a capacitor and the plates and the spacing and how does geometry affect everything. All right. And then after that, we'll talk about how, and that will relate to its length. And so that's kind of the geometry portion. We're also going to talk about how it relates to temperature. And I'm going to talk about these terms current and current density, and finally go into what they mean, the units and all that stuff, and kind of give you some basics on that. We may end up getting some electrical power somewhere in here. So power is kind of halfway between the two. And so then the next chapter, we're going to do sort of like what we just did for this quiz. You did a lot of capacitor stuff with series and parallel. We're going to do resistors with series and parallel and see what rules have changed, what didn't. We alluded to that last time. KVL and KCL, that's basically conservation of charge and conservation of energy. And this is called Kirchhoff's voltage law and Kirchhoff's current law. And we'll talk more about those in chapter 27. Finally, we'll get to what happens if you put resistors and capacitors in the same circuit, an RC transient circuit with a battery. Then we get into the harder chapters again, magnetism. And then, this is starting to get way ahead, but somewhere right around in here is where your oral presentation is. All right. After that, we do induced EMF and then AC circuits and inductors and RLC circuits and things like that. So that's coming way down the line, but this just kind of gives you an outline. What I feel is important is these chapters start to get hard again down here. So I want to keep pushing and try and cover as much as we can. If possible, on Wednesday, I'd actually like to start this chapter. So that's my goal is, and if you look at this chapter, I think there's only like 18 questions in it. I'm looking at chapter 26 right now. It's a shorter chapter. And I think you're only doing, it says up to 24 or something, but you're not even doing all of them. And so and this one doesn't have a lot of those fractions in it either. So let's get to it. All right. And so let's start with the screen share here. Let's go to this one. And then probably right about here. Chapter 26. Sorry, I was a little off. I should have had this up in advance. My bad. There we go. So we're going to start off by talking about resistivity and current, and I'll check the chat here. But yeah. Okay. No, I don't think so. Not when we do a third of them in class. So yeah. Yeah. All right. So in this case, we have resistivity and current. And now electric current is one of these really annoying things in physics. Basically, it's a thing in physics, right? So I just want you to read this carefully. In particular, this line right here. Current is not a vector. But you and I both are going to go through the rest of this course imagining current as having a direction, but it does not have a strictly speaking, it is not a vector. So just be aware. Everybody knows current has a direction, but the mathematical definition of it is just how much charge is passing a certain cross area per unit time. And that's what this picture is showing us here. So without further ado, let's just do 26.1 and get a feeling for the definition of current. You have a wire containing several moving charges. So each charge below is either plus or negative 1 nanocoulomb. In 1 second, all these charges flow past that cross-sectional area. So we got all these plus charges flowing past it to the right. And then we have the negative charges flowing past it to the left. So the idea is you have 6 nanocoulombs of charge per second. So we say this is 6 nanoamps. Now here's where it gets weird. Some of you might be saying, well, wait a minute, don't the electrons and the protons cancel out? No. So this is what's extremely frustrating. You have -2 nanocoulombs moving left. And then over here, you have 4 positive nanocoulombs moving to the right. And I just told you left and right doesn't matter. And yet it does matter, doesn't it? And so, strictly speaking, we can't think of I as a vector, but you can be damn sure you'd better think of it as a vector. What? I don't know. I don't know what to tell you other than negative charges moving to the left is the same as positive charges moving to the right. And that's what this question was supposed to point out. So current is not a vector. It's just the size of the net amount of charge flowing through there. And so that's why we get this funky number 6 and not 2. Okay. Questions about that? The moral of the story is don't think of it as a vector. It's a magnitude, I guess you could think. But negatives moving to the left are the same as positives moving to the right, and they add together. Know that.
Yeah. Yeah, my physics senses are tingling.
Yeah.
You have positive charges moving. Can you explain?
Well, maybe this happens to be indium gallium arsenide in their holes.
Holy crap.
So yeah, it turns out different materials, effectively the absence of electrons can move, and that behaves just like a positive charge. And those materials are called semiconductors, and those absences of electrons are called holes, and they move just like electrons, except they have a slightly different mass. So you could imagine an emptiness moving throughout a material, like a bubble moving throughout a material, except it's a positive bubble. Good enough, Ryan?
Yeah, that's really interesting. Okay, cool.
It is cool, and we can talk more about it later. So in practice, it is possible to have positive charges moving. And when we get to chapter 29, I will teach you about a test which allows you to see which type of charge are moving. So we'll get to that, or maybe it's 28. I don't know. Yeah. All right, cool. Other questions? Let's check the chat real quick. That's an S, right? This is an S. Hopefully that's what you were thinking. So notice a coulomb per second is equal to an amp. And I don't know if that's what she was asking, but let me double check if that was it. Yep, absolutely. Yeah, so a coulomb per second is called an amp. All right, so, or an ampere, which is just called an amp. We're going to run amp. There we go. So an amp is a coulomb per second. All right, good stuff. So that might be useful later on if we're looking at units and need to figure something out. Now notice this next one. Current density is a vector. What? Okay. Well, let's take a look here. This is the equation for current density. J is the current density vector, and dA would be this area right here that it's pointing. And so areas do, we could call this dA. The area vector, if you remember from Gauss's law, points perpendicular to the surface. And then now you could see how these current densities actually, if we think of current density as being the -2 per unit area, et cetera, moving on, this kind of makes some sense. Somebody unmuted. Was there a question there?
Yeah, I was wondering, does the dA go in both directions or just one direction?
You choose. And then, so for a flat surface, you get to choose. If it's a curved surface, remember, it generally, the default is to point radially out. So for a flat surface, why not align it in the positive direction?
Okay.
Is that cool? Yeah. Yep. All right. Very cool. Now check this out. If everything in this case had an I hat on it, right? So if this had an I hat and these have I hats, that accounts for the minus and the plus symbol. The plus and the minus I hat get right? You have negative charges moving negative I hat in the density, and so that gives you a plus. All right, so far so good. But notice the units of this thing, right? If we work all this out, the units should be amps per meter squared. Now notice one of the fun things about physics, this A is an area. This A is an amp. So remember, you've got multiple A's now all over the place. Areas and amps. You got to keep them straight. All right. So far, so good, I hope. Let's keep scrolling down the page and see. And by the way, we are on page 103. All right. So let's start with these and just try and get a feeling for this current density. So we're going to look at 26.2, and we're just going to kind of work our way down this page for a minute. And before we do this, I just want to tell you right now, we're not going to do a ton of stuff with current density. However, in chapter 29, we use it on almost every problem. So we should do these problems. We should learn this stuff. But if it doesn't make a ton of sense now, know that we will come back to it in 3 chapters. And remember, you can look at the solutions if I'm going too slow. So I'm going to start with this, what I see on my screen here. And I think for the most part, everything here we can use. All right. So we have a situation here where we could use this simplified equation and we don't need the integral. We can use this or this. So I'm going to get this drawn up on my page and you can do whatever you got to do. It's a marker. Okay. And then we have a so you remember maybe this is like the coaxial cable that we had. And so there's some shell and you have some current flowing through it. And I'm just going to try and match my solutions with the colors in my solutions. So give me a second here. It looks like I was going to draw blue. I don't know what colors I'm using. All right, let's go back here. All right, it's not really obvious. So let's say we have some current flowing this way. And remember, current is the symbol I, and technically I isn't a vector. All right. So we're figuring out the magnitude of current density here. Length is L, and then radii are R and 2R. Okay. So in this case, this shaded surface here is actually the cross section, right? So it's not flowing through a circular cross section. Oh, I'm not on my, sorry. So this section right here is actually the area where current is flowing through. So you could imagine there's all kinds of current flowing this way. Now, in this case, that area is going to be right? It's the area of the outer circle minus the area of the inner circle, which what is that? Just 3 pi r squared? So that's the area. So in this case, in this particular example, J, which is going to be amps per meter squared, don't overthink it here. This is just going to be I, which is the current, divided by 3 pi r squared. So it's a measure of how many amps per unit area. And that's it. Don't overthink it. That's current density. All right. I'm going to assume this might be okay. And I'm going to go to the next problem and look at it. So was I supposed, oh, that's all I had to do there. So that's not too bad. Now let's look at this one. What happens if it's non-uniform, which turns out can be actually pretty common? Fluid flow in a pipe is non-uniform, right? So it seems reasonable to think that electron flow in a pipe should be non-uniform. So now I'm going to look at 26.3 and I'm going to rework this, okay? Okay. We are told that. Got it. All right. So in this case, I've got the same shape, but we're told that the current density for some reason is alpha over r squared. What does that mean? The first thing I like to do is get a feeling for this. As radius gets bigger, the current density goes down. So that means there's a lot of current near the central part and not much current during the outer part. This could actually happen in a physical scenario if you had a beam of ions. So it's very possible and plausible to have a beam of ions where there's more charge close to the center than there is further out. So this is not an outrageous thing to think up. It might be kind of contrived since I just made it up, but in the real world, it's not impossible to imagine similar like kind of scenario. All right, whatever. In this case, what are we supposed to figure out? Total current. So maybe I want to find the total amount of charge per second. Well, then I'm going to go to my definition. And so now we run into trouble here. J, I know that. What's dA in this case?
Is it just pi little r squared?
Okay, so let me ask you this. Okay, so that was a good thought. We're on the right track. You're almost there, but no. So he said pi little r squared. Now, two things. I bet the vector you could figure out. Trey, what would the vector be?
Also I hat.
Yeah, because it's going this way, right? So that's easy. But now here's how I like to check these things. D area. That's got to be a tiny number. There's got to be a differential somewhere. So this can't be right because this is macroscopic and this is microscopic. Meaning a dA is something that's a tiny amount of area, a microscopic amount of area. This is a, yeah, so this isn't quite right. Does that make sense why it can't be right, Trey?
Yeah.
Yep. Okay. So any other thoughts?
Have with that?
What's that? Go ahead, Nick. Go ahead.
Just, I'm probably wrong here, but is it pi little r times dr?
I think so. This is the idea. Imagine if I tried to figure out this section right here. Right? And so think about this. Why did I choose that? And if I could, I'm going to bring it closer. Okay, why would I choose this little section in here? Well, because the current density is going to be the same at every single spot in this slice. So if I go around here, this would be 2 pi r. Wait, no, it would be, 2 pi r would be all the way around times dr. And I think, is that what you actually just said, Nick?
No, I said pi r times dr, but yeah, I meant 2 pi r times dr.
And yeah, so this would be the length all the way around that purple section, and that would be dr. And let me, just because my picture sucks, let me see if I can go to the solution picture, which might help you see this better. So that's where I'm at right here. Let me zoom in a little bit. It's that picture right there. So we're looking that thing, that little strip right there. Every point inside that strip has the same density. It does not necessarily have the same current as other chunks, but we're going to build up this toroid here, or this donut, out of all these rings. And so this particular ring has distance all the way around like that is 2 pi r. And that's where I got this right here. I'll pause for a second, or hopefully that makes sense, or you can read the solutions. And since we've got it here, I think the rest is all pretty easy. When you go, oh, there's a spacing there, but whatever. So once you get that, the rest of the problem is pretty easy. You just stick in some crap. Notice one of the r's cancels, so you're going to get a logarithm, and then you're going to evaluate it at the limit, so you get log 2r minus log big R, and then you're going to have, you could do the division, and so we get this result right there. Not too crazy. Wait a minute, check the units, right? So let's do that and see how would we check the units. Well, I go back to the original density equation, and I see that alpha has these units, which alpha has units of amps. So, or going back to this right up here, right? I know this has units of amps, and this has units of something. Wait, this has units of amps per meter squared because it's a current density. And this has units of meter squared on bottom. So clearly the units of the top have to be amps. All right. All right, so far so good. I told you 20 problems wouldn't be that bad. What else are we doing here? I think that's it for that one. Okay, so now we've seen current density, and just try to get used to this. Current is not a vector. Current density has the vector portion in it. And also you could see what happens if we have to integrate this thing. Let's do one more and see, okay? And I think you'll see why current density is something that's non-trivial in this next one.
I think
go ahead.
I don't know why, but I'm a little bit confused still about current density having direction. I don't know.
And current not?
Yeah, I guess, kind of.
Let me ask you this. Do you intuitively feel like current has a direction?
Yeah, like it travels.
Yeah, exactly.
Yeah.
And so
Okay.
do you agree that it would be natural to think that current density also has a direction?
Yeah.
And so the idea is, for some reason, the strict mathematical definition of current is take the absolute value of doing this current direction.
Okay, so a better way to phrase my question is probably then, why does current not have direction?
Yes, and that
okay.
is just because that's the way people decided to do it.
Gotcha.
Yeah, cool.
Yeah, I think that's good.
And
yeah.
one of the things, you're going to hear me say this over and over and over again for the next 2 weeks. I'm going to say, which way is current flowing? Which way are charges actually moving? And that's the question that relates to this. And then just know that we consider I to be a positive number. Just like in a lab, you may have noticed I was ignoring minus signs sometimes on numbers in the lab when we did it a couple weeks ago, or was that last week?
Yeah.
It's the same kind of thing where we just were like, just give me the size of the current, right? Just give me a number for how much charge is flowing per unit time. And the directionality absolutely matters in the real world, especially if you bring in just the simplest device like a diode. A diode allows current to flow one way, but not the other. So that means it has basically negligible resistance when current's flowing to the right, but infinite resistance when it's flowing to the left, but it's complicated.
Okay,
Is
cool.
that enough on that for now?
I think so. Yeah, I understand that a little more now.
Yeah, I always think about current as having a direction as well, even though strictly speaking, you're not supposed to. So Sam, L is not considered in the area because of this. It's the cross-sectional area. We do not want the surface area. We're looking for the area through which charges flow. So in this case, charges are not flowing through the sidewall, and so that length L never has anything to do with it. The length L absolutely is going to matter on the next page when we talk about resistance. So the longer a pipe is, the more there's friction with the walls of the pipe, the more you have drag. Similarly, the longer a wire is, the more resistance you have. but that's not what we're talking about. Sam, did that address your question? All right, cool. Yep. So now look at this one and we'll see. And I think this is enough to kind of get you rocking on current density until chapter 29. Say you have a metal pipe, you got this inner radius, outer radius. Now current is flowing radially outwards. Okay, so this is possible, right? You've seen this. What if you had the inner conductor has some positive charge and the outer conductor had some negative charge or something, right? It's possible. You could imagine current flowing from the inner surface to the outer surface if you connect the positive terminal of a battery to the inner, okay? All right, and now total current is I. Now look at this. Where is current more dense? Near the inside wall or the outside wall? Or is it constant? Total current is I. Is current density uniform or not?
Non-uniform.
Mm-hmm. Where is it stronger, or where is it most dense or more dense?
Nearest the center.
Yeah, exactly. And so the same amount of charges have to flow through. So if I could blow this up, if I was going to be a charge flowing through here, right? Oops. Right. If I was going through that surface versus that surface, right? The same amount of current is flowing through the red and the purple rings. So clearly there's going to be more charges flowing. Whoops, get rid of that. There's going to be more current density on the red ring, right? Because the current lines are closer together, basically. So we see that the same shape can have different current densities and different currents depending on not only whether it's uniform or non-uniform, but also which direction the current is flowing. All right. And so just be aware of that. And I think that's pretty good for that. Let me get this smaller again. Oh, whoops. All right. Like I said, chapter 29. There we go. So that's when we're going to spend a lot of time on this. So notice we used charge density when we did Gauss's law. Later on, we're going to do a thing called Ampere's law, and we're going to use current density. So until we get to that point, let's just kind of, let's do that. Any questions about current density before we go on? Okay. I'm going to keep moving at a good pace, so stop me at any time if I race ahead too far. Now, a common thing that people think, they confuse current with electron speed. So now, as Ryan was saying, normally we have electrons moving in a wire. I think it was Ryan or whatever. But so I just want to point out that the speed of electrons is not the same thing as current flow. They are actually extremely different. Also, notice this keyword drift speed. Now, I am going to be straight with you. This page 104, is very good for physics majors and electrical engineering majors, and probably, notice this number of moles appearing, chemistry majors. I am not going to test you on this page. I think that's clear enough. If you're a physics major or an electrical engineering major and you don't do this page, you're probably going to have trouble later. Now, all I'm asking you to do is walk through. It's a worked example, and this is what's really interesting. Let's get down here. Relate current to average speed. Okay, blah, 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 blah. If you have a 15 amp current running through a sheet of aluminum foil, so now think about, I'm putting the sheet of paper, or whoops, aluminum foil like this. Let me stop this for a second. So, right, imagine this was a sheet of aluminum foil. And I think I said it was about 3 centimeters by 3 centimeters or something, right? Whatever. So it'd be a pretty small sheet of paper, or sorry, aluminum foil, and it would be very thin. Okay, so it would be a very thin sheet of aluminum foil. If you had such a piece of aluminum foil and you were running 15 amps, that's a big current. That's a big current, okay? That's like, right, most household circuits have breakers at 10 amps, except for maybe 20 for the kitchen, okay? So this is a pretty big amount of current, okay? Maybe 20 amps, depending, yeah, blah, 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 blah. Look at this speed. Look at that speed. This is what's interesting about this. This is called the drift velocity or drift speed, and we see it's 2.6 millimeters per second. These electrons are not moving very fast, are they? On average. So here, let me try and simulate this for you. Let's say we have a wire like this. So let's say that's a wire, and let's say this is an electron here. Let me, okay, hopefully you can see these squiggles. The idea is the electron is actually moving extremely fast, but it's going like this all the time. So I don't know if you can see my pictures being drawn, and it's slowly working its way down the wire. It's not staying in there very well, is it? But you get the idea. So the idea is the electrons are moving tremendously fast, but they keep bumping into things on the way. And they only move at an average rate of 2.6 millimeters per second for this particular sheet of aluminum foil. Moral of the story, okay? Moral of the story is these electrons are trying to go down the wire, but they go forwards and backwards, and sometimes they go really far and then backwards. And so as they try to go down the wire, they're barely getting anywhere. On average, they're only moving a few millimeters per second. All right. Questions about that? If you're an electrical engineer or a physics major or maybe a chemistry major, you should do that page and follow it through and do it. Okay. You'll see that in the book, not on the test. Got it. It's pretty cool, though. That's kind of a brief introduction to some terms that we needed and some concepts that we're going to use later. Now we're going to get into the heart of this chapter. Page 105. All right. I see this every year. Every year. You should pay attention right now. Resistance and resistivity are not the same thing. Okay? Resistivity is a property of a material. Resistance is the property of an object. And so what do I mean by that? A chunk of gold, and any chunk of gold has the same resistivity. Just like every chunk of gold has the same density. It's the density of gold. Okay? Whereas resistance depends on the shape. So you could talk about intrinsic and extrinsic, blah, 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 blah. But I guess here's what I'm saying. Gold has a mass density. Every chunk of gold has the same mass density, but every chunk of gold has a different mass. Similarly, every chunk of gold has the same resistivity, but a different resistance. So to get the resistance, you could use a DMM and just measure it. But you can't really do that for the resistivity. How do you get the resistivity of material? I just wonder what we're doing in lab tomorrow.
Fully divide out the volume?
Yeah, we'll get to that in just a second. So let's get to the equations. Good question. All right. So now, oh boy. This sigma and this rho are totally different than the sigma and rho we used earlier. Sigma is now conductivity, not surface charge density. Rho is going to be resistivity, not volume charge density. How do you tell the difference? Well, if you're doing a problem that's got Gauss's law crap in it, sigma and rho relate to charge densities. If you're doing a problem about resistance and lengths of wires, sigma and rho relate to conductivity and resistivity. This is Ohm's law. This is the right way to do Ohm's law. Now, most of you probably know it like this, which is more practical. It turns out these two equations right here are actually one and the same. This upper one is the full vector, and here this is called a conductivity tensor, right? Tensor, yeah, whatever. Don't worry about it too much. It's basically a matrix, okay? So if you want to know more about this up here, talk to me later. The fact remains, why am I even mentioning this at all? Here's why. In some materials, they are anisotropic. I love pronounced not on the test. That's a good way to pronounce it. Anisotropic. Sorry, I made myself laugh there. But yeah, the idea is in certain crystals, it's easier to conduct electricity in the X direction than the Y direction. If you've had a materials class, maybe you've seen this before. But so if you're into material science, you probably will need to know this eventually. Or if you're an electrical engineer, this is a cool thing. You can use directional conductivity. So it's easier to pass current in one direction than another. You could make a useful device. This would be for isotropic versions. This is fine for us. So this equation is a good one right here. Let me clear this out. So this one, if you really had to, you could just scratch it out and not read it again. All right. This is one version of Ohm's law. This is another version of Ohm's law. These are the more common ones. So Ohm's law basically is a relationship between voltage and current. Well, you could also think of that as being a relationship between current density and electric field. They're very, very similar. All right. Now, resistance depends on area and length, and you've got to be falling asleep by now. So let's go to a quick simulation here. Is this the one? All right. So here's the idea. Resistance is rho L over area. So resistivity, as I increase this, you notice that the number of dots in the material is increasing. The number, think of those as impurity atoms. So in this case, if you have a very low resistivity, you're going to have a very small resistance. Now imagine let's increase the length of this too. Let me get off my zoom there. So what if I crank up the length? All right, so here's a very long wire. Obviously, if I'm an electron trying to get through here, right? If I come along, I might hit one of these atoms and bounce around, right? And so as I'm trying to get through here, the more of those impurities that are present, the harder it is. So if I have more impurities in the crystal lattice, it's going to bump around a lot more and take a lot longer to get through there. That's basically a larger resistance. You can think of resistance as drag, right? The more resistance you have, the more you slow down or impede current flow. All right. Now, similarly, if you use a bigger pipe, if you use a large area, it should be actually a little bit easier for electrons to get through. So maybe you have more than one electron traveling at once, right? So now the bigger area, the easier it is to get more and more electrons through. So that's why area is in the bottom. I'll pause for a second. Any questions on that? Hopefully that gives you kind of an intuitive feel of that. All right. All right. And so just think about this. What we did just a chapter ago or 5 minutes ago, or whatever that was. All right. And so here, I just want to point out the differences between a resistor and a capacitor. All right. So notice the area is on top in a capacitor equation for parallel plates. All right. So in this case, if you have more area, it was easier to store charge up there. And then also, if you had a smaller plate spacing, the closer they are together, it was easier to store charge. Now, resistance is trying to impede current flow. The longer the pipe, the more likely you are to hit impurities, the more resistance you have. The more impurity density you have, that's what rho is. And then area, the cross section, as you make the area bigger, there's actually more paths to get through successfully. So it's a little bit easier. There's actually less resistance as your area goes up. And you can see, because the area is flipped in a chapter, when we look at the series parallel combination rules, those are going to flip. And just likewise here, D, you could think of D as something kind of like length. So because the areas and the lengths are flipped in the equations, the rules for combinations in series and parallel will also flip. All right, so just wanted to mention that.
What's C?
C is capacitance.
All right.
Sorry, this was sorry, I'm mixing chapters now. So this was chapter 26, this was chapter 25. My bad. Yep. Good call. Good question. All right. We finished this one now. All right, so here's Ohm's law. So now we're kind of getting closer and closer to circuits here. So in this case, obviously, the more voltage you apply, the more current you get, right? Similarly, if we lower the resistance, are you guys able to hear those spacey sound effects that are jamming out in my brain? It's really crazy. I hear these weird spacey sound effects.
Like as you move the
Yeah, as I
simulator?
move the sliders. Do you hear those?
No, we don't.
Oh, yeah. I'm like, man, it goes like. Yeah, anyways. So if you guys want to check these out, let me, I tell you what, before I do this, let me find, hold on. I'll put this in the chat in case you want to play with them, okay? Where is the chat? Where's, that way you could play with these after class and you could trip out on those cool. There's all the different electricity and magnetism ones. Yeah. So that's if you need that. Okay, great. So that's right. You definitely need that. And then make sure you drop about 6 quarts of acid right before, because that's what I did. Quarts. That tells you how much I know about acid, right? All right. So let's see. What was I doing? Ohm's law. All right. So in this case, it's a very similar relationship. You guys are pretty good with linear relationships here. So there we go. But yeah, I do want to point out that the current flow is going to ultimately relate to resistivity as well. So let's leave that in there and leave it at that. All right. So far, so good. We're just kind of getting a feel for how these things all relate. Let's get back to here. All right. And so, poison ivy. So P is going to be, this is called a script P. So I call that script P. Yeah, script P is the power delivered to a resistor. In the old days, it used to be dissipated by. So this is the old phrasing. If you read old textbooks, they might still use that. I could care less if you use dissipated by or delivered to. Yeah, that's right. Okay, now, finally, we have a couple more questions, and then we're done with this chapter, or a couple more equations. So these equations right here talk about resistance and its relation to temperature. And so I do want to point out specifically, resistivity will change with temperature. In turn, if you just take this equation and stick it in right there, you get the other equation. So these two equations are essentially the same thing. It's just resistivity is affected by temperature. Now, it sometimes goes up, sometimes goes down, right? Most metals have alpha greater than 0. So typically when you heat something up, the resistance goes up. If you've ever heard the term hot starts, where it's difficult to start a car, maybe it relates something to that. However, semiconductors behave exactly the opposite way. As you heat them up, they become better conductors. That means their resistivity goes down, which means alpha right here has to be a negative number. So now, be careful. This is, okay, Luke is bringing up some great points in the chat. For whatever reason, see this number 0 here? That means at 20. So typically 20 degrees Celsius is pretty close to room temperature. So if you go below room temperature, your resistance usually goes down. But for semiconductors, as they get cold, they actually become worse. And so resistivity doesn't become negative, but there is a small change. Is that making some sense? Superconductors are their own thing. So superconductors are, don't think of them as resistors, really. Yeah. What I would say is a superconductor expels all external magnetic fields. It's a perfect grape, don't you know? Grapes are diamagnetic. Water is diamagnetic. Superconductors are perfect diamagnets. That's really the property. A side bonus, 0 resistivity. So the resistivity is not the fundamental property, which wasn't, yeah. So I'll show you that some other time. Let's do superconductors later. So notice there's semiconductors. Semiconductors are carbon, gallium arsenide, indium gallium arsenide, silicon, right? And so those are the kinds of, I mean, these semiconductors are really, really important. Most of this class, we will focus on metals, except for maybe some concept questions about this. You better have this shit memorized, people. You'd better have this memorized, this line. I expect you to know that semiconductors have alpha less than 0, whereas everything else is pretty much greater than 0. You should know that. All right. Yeah. Okay. So that's pretty good. Whoops. We're about ready to start doing some problems, but we're about ready to take a break. So I think what we should do is we've kind of introduced these concepts. Let me do one more thing really quick. I've got it here. No. This one. Let's do this and then we'll take our break, okay? And so here is a simulation showing the electrons flowing, all right? And let me get this moved down here. I'm going to use some green here. So notice this pinwheel spiraling around here is showing you a speed. It relates to the speed. Now, it's not exactly the same thing as the speed, but it relates to it. That was that current density crap that we talked about. So that's the current, the amount of charges passing that pinwheel at any given time. And notice inside of here, these green particles are supposed to indicate impurities. And so as the electrons try to move through this, they're going to bump into those. And we see that the density of the electrons in that material is going to be somewhat non-uniform. But if you multiply this by a mole of electrons or 10 moles of electrons, you're going to have lots of electrons moving all over the place and lots of impurities. And so now what I'd like to do is I'd like to up the voltage for a second. So watch what happens as I up the voltage. Notice, what do you see happening? It's getting warmer. That thermometer scale down there. And so as these things get warmer, notice the green balls are wiggling faster. And that gives them more thermal energy to smash into the electrons and slow them down. This is the basic principle behind why most materials, most metals, as you heat them up, become as you heat up a piece of metal, its resistivity increases. Okay, so what am I saying? So rho is equal to rho at room temperature times 1 plus alpha times T minus this reference temperature of 20, which everybody decided to agree on room temperature, 20 degrees Celsius. And we see that for metals, most wires are made out of metal. Alpha is greater than 0 because as you heat it up, these green spheres in here have more kinetic energy to impede the motion of the electrons as they try to transit. All right. Now, if you did this with a semiconductor, it's a little bit different. And in fact, well, it's the opposite. So with semiconductors, as you cool them, they conduct electricity in a different manner, and we don't want to focus on that right now. So let's go ahead and crank this all the way up, because why not? If we crank this all the way up, oh, let's make this white hot. Let's make this resistance even smaller. So there we go. So you can see that, oh my gosh, this wire is about to melt. All right, so let's calm this down. And then this is a good point to bring up. Well, wait a minute. Oh. We'll go right to there. So in this case, I want to point out one other thing before our break. This is the positive terminal of the battery. Over here is the negative terminal of the battery. I noticed that these are electrons. Remember, these are electrons are moving this way. And notice here, the electrons. And so outside of the battery, we see that electrons are being pushed away from the minus towards the plus. That begs the question, why does that still work on the inside? Well, let's look inside the battery, shall we? Magical fairies. Magical fairies are clearly doing all the real work. Magical fairies are another name for chemistry. So if you want to know what's going on inside a battery, take a chemistry course and don't talk to me. Yes. All right. So hopefully that's a little bit fun. Let's take a quick break here, and we'll come back and do problems with this afterwards. Okay. So give yourself 7-8 minutes here, and then we'll come back. All right. course. Let's catch up here. Magic, fight me. All right. Thallium burger. The old thallium burger. All right. Oh, good. All right. Oh, man. Let's see if we can, we've kind of talked about these topics and maybe, you know, thought about them. Are there any big conceptual questions before we get right to this and start doing problems? And you could ask them once we do get into it as well. All right. Let's get to it. So, all right. Let's get rid of that. Let's get rid of that. Let's get rid of that. All right. So just a reminder, we're going to try. So the problems that we're going to do now, this is kind of the guts of this chapter. So we're going to be doing page one. Use the equations on page 105. So keep that dog-eared if you need it. So just keep flipping back to this page. And I cannot stress this enough. Whoa, that's double at. That's an at. All right. So here, for some reason, we chose instead of 0 degrees Celsius, everything's going to be at room temperature reference. So everything is referenced room temperature. I don't know if you care. By the way, the units of this thing should become evident, but maybe I should mention the units of this thing. We know that this entire thing has no units, right? How do I know that? Because the number 1 has no units, which means this has to have no units. All right. And so notice that the units of alpha are going to be 1 over degrees Celsius. And you could be one of those people like, shouldn't it be Celsius degree? I don't care. All right. So notice that's the same thing as 1 per Kelvin. And if you don't know what a Kelvin is, that's okay. We're not going to use that. That's the subject of 162. If you did this already in 162, you know that degrees Celsius and kelvins are the same increment size, so it doesn't matter. But this temperature here is going to be in Celsius. All right, in Celsius. So we're not going to use Fahrenheit. All right. Not Rankines either. All right. Oh, okay. I forgot this. So 106, page 106. If you need a little mnemonic device for keeping these together, I'll show you this. Nobody calls this the Chacho method, only me. Okay. It's just because Chacho was one of the students that told me he liked this. I needed some name, and this was his real name. I still don't know how to pronounce that. So Chacho, if you're out there, what's up, man? Thinking of you. All right. So let me show you how these work really quick too. It's just a quick device. If you haven't seen these, it's right. I just remember Q equals VC, or I have an equation sheet. But now if you look in this one, let's say we have delta V equals, wait, what is it? Q. So if you're trying to solve for charge, it's going to be VC. If you're trying to solve for voltage, you put your hand over it, it's Q over C. Do you see that? Q over C. And if I'm trying to solve for C, it would be Q over delta V. And so this is just a way to keep that straight. Similarly, delta V equals IR. Sometimes I'll use lowercase I for current. Let's use uppercase for now. Okay, so V is equal to IR, I is equal to V over R is, and so if this reduces your mistakes, just draw this on your paper or whatever. If you want to use that, that's great. Okay, let's get to the questions now. All right, and there's one for poison ivy too. All right. Twinkle, twinkle, little star. Voltage equals I times R. All right, finally. Geez, let's get to this. 26.5. Okay, so I'm going to write it down. You get what you need. I'm going to be sloppy with the sig fig. Sorry. Notice I use little r for the radius now because capital R means resistance. Isn't this crazy? It's like every single symbol is used twice in this class. And this will give us a chance to get used to these units. Boy, this is yeah, okay. And so you've got the solutions too, but maybe it's worth listening to me a little bit right now. Okay, so in this case, look at these units. I just want to point out, these are not ohms per meter. The most common thing students screw up is they'll say ohms per meter for this. No. Ohm meters. In this case, nano-ohm meters. All right, so don't overthink it. I know that resistance is equal to rho L over area. Most resistors are cylinders, all right? There's some kind of cylindrical wire. Most wires are. So in this case, I'd expect the area to be what? What's the area? Remember, it's cross-sectional area.
Be pi r squared.
I thought they were round. Oh, okay, yes, very good. Pi r squared. Just, oh my gosh, I'm losing it. Sorry, my bad. At this
That
point,
took me so long to get.
Yeah. It's pretty bad. It's right up there with what do you get when you cross a grape with a mountain climber? Are you crazy? You can't cross a grape with a scalar.
Yeah, I remember that one a year ago. Oh my gosh.
Yes, that one's on fire. Okay, let's see. Let's go to the solution and take a look at the answer here, because we've got it already figured out. Okay, there it is. Is this the one? And so it looks like I got 31.07 milliohms. And so that's just plugging in all these numbers. I think you could check that out and make sure you're getting your prefixes right. Oh, that figure got a little quirky here. That's strange. Whatever. It doesn't matter. I'll fix up. I better make a note or I'll forget. What is that? Quirky figure. 26.5. There's another one that was quirky earlier, but I don't know why it got shifted like that. All right, whatever. Okay, hopefully you had a chance to do that. So all right, now let's go back. All right, so that was equal to, I figure you can handle prefixes. Next, what was the next thing? By what factor should we change the length to decrease the resistance by 5%? So that's what this question makes me think. In part B, I want R prime to be 5% less. So 5% less would be 95% of the original resistance. So in this case, I would just do this. Rho L prime over area. We're only changing the length. Or you could take a ratio, right? But in this particular case, I'm assuming that the areas don't change. I'm assuming that the resistivity doesn't change, but the length does change. I could see, oh my gosh, if I make it 5% shorter, I get 5% less resistance. Not that exciting, but this does foreshadow the next part. I'm going to go right to it. How about the radius? So by what factor must we change the radius? I can already tell this is going to be a little bit sneakier. Okay. So we'll go to part C now. All right. Oh, and let me get the chat there. And let's take a look. You might be, I don't know, Jaden. I don't know. Because it's not changing by a factor of 5. It's changing by a factor of 0.9. Yeah, so it's not going to be that, I don't think. So I can tell you this. I want R prime to equal 0.95 of R. Right? Decrease. Okay. So I want this to be true. I want the resistivity to remain the same, the length to remain the same, but I want the radius to change. So that's going to be different. Area prime. In this case, those drop out. And notice I could see, let's say, area prime. And we got to be careful here. Make sure I didn't flip this. So this would be A over A prime equals 0.95. Flipping that, A prime over A is 1 over. And notice this is not the same thing as saying it equals 1.05. It's different. Okay. So yeah. Now in this case, now I'm going to plug in what I know. Pi radius prime squared over pi radius squared. And the pi's drop. I could drop these if I take a square root. And so that's what it is. I need to increase the radius by that factor, which when I plug that into my calculator, if I can find it, oh, there it is. One divided by 0.95 and then square root it. 1.026. That's not what I want to write on the whiteboard with. Is that right? So 1.026. Let me check that. Yep, that's what I get too. Looking good. All right, and so the idea here is notice a couple of things with this. It seems really simple. Some of the questions are really simple. A lot of what we've done today are simple, but every once in a while, there's a sneaky little piece in here. So don't get lazy on me. Make sure you actually do the homework and get caught with the little tricks doing the homework rather than getting caught on quiz day next week or whatever that is. Okay. So, and this is something else. Notice there's a difference between dropping something by 5% and saying something else gets 5% bigger. They're not the same. Right? Increasing the area by 5% is not the same thing as decreasing the resistance by 5%, because we get this 1 over this. If you 1 over this number here, right, it's not 1.05. It's approximately 1.05. So, right, I got that top number, 1.053. So there's a difference between saying the area needs to get 5% bigger and saying the resistance needs to get 5% smaller. And I have no idea if this would ever come up on a Canvas situation where you're off in that third sig fig and you end up missing it because you said, it should be about right. So just be aware, there's the way things are, and then there's very good approximations. All right. Saying the area gets 5% bigger is approximately right. But the more you increase that percentage, the worse that approximation gets. Increasing the area by 1% is almost identical to 4 sig figs to reducing the resistance by 1%, but 5% not quite. All right. All right. Approximately, and notice it's not quite 2.5. It was 2.6%, right? And so we see there's just that little, in that third or fourth sig fig, things change. And so that's where the square root. And so, yeah, just be aware because of these squared relationships and inverse relationships, don't just make a guess, write it out on paper and scribble it out really quick and you'll get it right every time. Okay. All right. Yep. All right. And so let's see where we got on that one. Good enough. Okay. I'm going to let you guys try this one at home and this one at home and this one at home. So these are good questions and you can go through those and do, it'll force you to get the units and stuff. And that's stuff that you're going to be better suited to getting at home. We've done a little bit already. This particular one, I'm going to let you guys do that. I'm just looking at the time. Okay. So I'm going to let you do up to 26.9 at home on your own. A lot of those have numbers and students tend to be better with that. This is really cool. Old side note. Turns out originally in Europe, they used osmium filaments, which osmium is this extremely dense material. It's more dense than gold in certain cases there, depending on the isotopes, et cetera. But yeah, they used to recycle the light bulb filaments. It's pretty crazy, right? Of course, now we just take everything and throw it in the garbage. All right. This is something I want you to look at for tomorrow's lab. All right. So 26.10 and 26.11 relate to tomorrow's lab. So why don't we just at least get a start by looking at this thing, and maybe that will reduce some of the confusion in lab. So 26.10, all right? So we have a cylindrical wire with this resistivity. We're going to measure the resistance between the two ends of the wires, and we're going to plot resistance versus length. This sounds a lot like what you're supposed to be doing in lab tomorrow, okay? So now in this case, for this particular problem, in this problem, I gave you the resistivity and we're going to figure out the diameter. I think in tomorrow's lab, I gave you the diameter and you got to figure out the resistivity. So it's not exactly the same, but it's pretty darn similar, okay? All right, in this case, whoa, any thoughts? I guess without looking at the solutions, any thoughts what you might do? There's lots of different ways you might try to do this.
So since we can measure R experimentally, you can try a bunch of different lengths and then pretty much use that formula to solve the resistivity at different lengths.
You could do that. And you might guess that's not what we're going to do based on the way I said that. That is a great way to do it, Trey. I'm not going to lie. It's a good way. I'll say it that way. Yeah, and so if we do this, just give me a second, and kind of eyeball it. That looks too high. That looks right there. So if we do a trend line, it turns out we make less work for ourselves and get a more reliable number and make the error analysis easier, which you have to do tomorrow. So all those are the reasons that we're not going to do exactly what you said. But basically, if I understood what you said, Trey, you're basically making a table for each of these points, plug it in and get row for each one and average them, right?
Yeah.
Yeah. And that's pretty much what we're doing when we do a linear regression here, or basically do a trend line fit. The cool thing is if we do that, we could get the slope here. And so from this, let's just see, notice I want to write something here. This is where I want you guys to get good because this relates to general engineering principles. Y is equal to slope times X plus intercept. That's how I'm going to write it. All right. Now, in this case, hopefully you agree that the intercept is 0. And I want you to help me, or well, maybe not. I'm just going to do it for you because I'm tired. Okay. Notice that the Y coordinate is resistance. Watch those units. Notice that the, ooh, let's see. X, let me get a different color here. X is what up here?
Millimeter length.
The length in millimeters. Let me do this. Hold on just a second. So if y is this and x is that, what is the slope? Whatever's left, right? And so now we just figured out that slope is equal to rho over area. And then for us, this is a cylindrical wire. What is the area?
Pi r squared.
Yep. And then notice this problem says diameter, so that's going to make us change it to
1/2 d squared.
how about I write it like this? Pi over 4, because you're going to square the 2,
Yeah.
right? And there's a rho. Well, wait, isn't that going to be just, I could move the 4 up top to make it cleaner, and then it's that. And I just want to point out that this, everything that we've done so far is still very similar to tomorrow's lab, okay? So in this case, we see that you've got the slope of your plot is going to immediately give you a weighted average for the diameter or for the resistivity, whichever thing you don't know. And so this gives less credence to these outliers. And so it's a slightly improved way of weighting your averages, Trey, compared to what you were suggesting. So that is kind of the sketch of that problem. Let me pause for questions. Any questions? Outstanding. And yeah, and the other way that Trey suggested is actually good. I think this way is slightly better, but yeah, anyways. All right, let's go. Whoops. And that's a lab technique, right? That's why we're doing this in lab tomorrow. So let me get down to there. What was this one? Oops, we're at the next one. Sorry about that. Okay. Now my method has a warning attached to it. So remember, the slope method is only going to work if the plot is linear. But similarly, that other method would only make sense if the data was linear, right? So this is what I discovered. People just pick a random point and plug it in. That's not a good strategy. If you do every single point and average them, that's good. And then if you do the slope method, I think that's slightly better than either of those. All right, so we just kind of walked all through this. So that kind of gets you rolling. All right. So this gives you some side notes there. I don't know. I'm going to let you work that out on your own here. Let's go to the next one just because that is, okay, so this is copper or silver. Ha! Oh my gosh, that's a big big diameter cable. A copper or silver cable that's 1 inch diameter. That thing would be very valuable. All right. Okay, let's go back to here. I'm entertaining myself. All right. Let's look at this one. This is a different plot. All right. So notice you're going to see this for the rest of the semester. It's going to be crucial for you to look carefully at plots and understand them. And I think that's true of any scientist. You need to have good graphical literacy. Understand things like what does the slope mean on every plot? And what are the units on every plot? And just be screwed over so many times as an undergrad that you just always look at everything. So let's do another one. Notice now we're doing current versus voltage. All right. And so in this case, if I want to get the wire's resistance at standard temperature, let's see, resistor's temperature. Notice the curve bends at high volt. Okay, so right here, for voltages above 4, we see it gets hot. All right. Now I'm just going to do a quick unit check on this right now, everybody. In this case, let's see. What would the slope be? Give me the units of slope here. going to be rise.
Yeah, amps
Overrun.
over volts.
Yeah. So what is that? Milliamps over volts. Let's go take a look. Milliamps over volts. Oops. Do you guys have any equations that relate amps, volts, and resistance? Do you remember any?
The voltage Ohm's law.
Yeah, the Ohm's law. All right. You could use uppercase I, lowercase I don't care. All right. In this case, just don't use I hat. So let's see. We said, what did we say we had? Ohms? No, we had milliamps over volts, right? So isn't that equivalent to current over voltage? So let's rearrange this and see what we get. That's 1 over resistance, not resistance. For all you electrical engineers out there, this is the standard way. Why? In math class, you probably know on the x-axis, we usually put the independent variable, which the easiest thing to control in most experiments is the voltage of a power supply by turning the knob. Then we measure the dependent variable or the current. And the idea is you change your power supply voltage to different levels, basically like putting different batteries inside of a circuit. You put in a 1.5 versus a 2.5, et cetera. That's what we're going to do tomorrow. We're going to sweep the voltage and we can see what happens to the current. From that, I see there's an inverse relationship. At any one point on the plot, so this is that attempt to draw that plot. At any one point on the plot, I could take the current value and divide it by that voltage value, and that's going to give me 1 over the resistance. All right, fine. And likewise, if you wanted to go here, you could say resistance is equal to delta V over I. Now you have to know, basically, this is the standard way plots are made, and everybody makes them that way because this is what usually is controlled by an engineer. In this case, what else did I want to say about that? This would be true wherever you are. And now notice this particular plot. This is not linear. Okay, so if you try to do the trick that I just suggested on the previous problem where just take a slope and average it, that's not going to work. It would work for this region of the graph. So we could do the same thing that I was talking about last time where you take a slope and do all kinds of things and get an average and blah, 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 blah. All that stuff would work over here. So in practice, what is going to happen tomorrow? I know it's time to go. This is the idea. I had to use a power supply and I recorded the voltage across the power supply and the voltage across a resistor. If you know that resistance, you could figure out the current. That's going to help you figure out the resistance of this other resistor. And then we're going to see how that resistance changes versus length. So we're going to be using both this voltage idea and we're going to use this equation. Let me do it like this. We're going to use this equation, Ohm's law. We're also going to use this equation. We know that the area for cylindrical wires is going to be pi diameter squared over 4. And what else do we know? I don't know. There's maybe a couple other things. I'll remind you about this tomorrow at the start of lab. But the idea is in your write-up, I expect to see you explain these 3 equations because these are the 3 that matter, right? So you'll see when you have to write a report on this, make sure you mention these 3 equations in the introduction and I'll be happy. All right. I think, yeah, and there might be a couple other things and we'll have to draw the circuit and stuff too. Let's go ahead and call that a day and worry about lab tomorrow. but try and get those problems done 26.10 and 11 before lab tomorrow. Okay. If you have the time. If you don't, that's fine. You can still do it. It's just you'll understand more.